Okay, today we're doing the new problem of induction. It's not easy being grue. This formulation of the same problem is due to Nelson Goodman, by far the most recent of the philosophers we've talked about in this course so far. This gentleman passed away just a few years ago, but the work this lecture is based on is from must have been fairly early in his career in the 1950s. So Goodman's starting from the same place as we are in the course, which is to recognize the fundamental problem that there's no system for inductive logic. So he says, principles of a deductive inference, we have the familiar and highly developed laws of logic. That's what we've learned so far. But there are available no such precisely stated and well recognized principles of inductive inference. Okay, so he's setting up the problem. That's the problem. Why we've been trying to discover these stated and well recognized principles. What Hume has shown us and what Goodman will attempt to re-explain to us, perhaps in a more comfortable way, is why there are no such principles. So, induction, the way Goodman wants to think of it, is generalizations confirmed by their instances. So, for instance, this emerald green, right, if someone were happen to be wearing one, that would be a single instance of the generalization, all emeralds are green. And the reason we think all emeralds are green is because of the very many instances that we have observed. And we would have lots of smart things to say because we're good critical thinkers that we'd want a diversity of sample, not all emeralds from just one place, not just one jewelry store. We would want to sample emeralds from a wide range of places. We'd want lots of them, not just a single example. So we want to avoid bias. We want to avoid inadequate sample size. And so if supposing that we have lots of instances and we have a good diverse sample, this seems like a pretty good inductive argument that all emeralds observed to date are green, therefore all emeralds are green. And there's nothing wrong with that. That seems like as good an inductive argument as we're likely to get. But we could formulate a very similar argument that we're not so sure about. So let's define, and this is Goodman's sort of key insight, define grue as green when observed and blue when not observed. And then we would say this seems like an equally good argument. All emeralds observed so far are green, therefore all emeralds are grue. Now, the premise is exactly the same as this argument, right? All emeralds observed to date are green. All emeralds observed so far are green. Obviously, nothing wrong with the premise. Two different conclusions. And we want to say, so what's this grue business again? Let's remind ourselves. Grue is green when observed and blue when not observed. So we've got lots of evidence that emeralds are green when observed. And the blue when not observed, it's hard to see how we would get evidence against that. So what do we think about that argument? And if this were a live class, we'd probably have something of a discussion as we tried to pick this apart, because most people want to say this all emeralds are grue is a load of hooey. That there's something fundamentally wrong with that. That this argument is good, all emeralds are green, yes, totally agree. This argument, starting from the same place, the same evidence, and just a slightly different definition in the conclusion, and we want to throw it out. So I'm going to try to sort of anticipate the questions that would likely come from you as you're thinking about this. And so let's work through that. Almost for sure, someone's thinking right now, look, the problem with that argument is that grue is just a made-up word. I never heard of grue before. If I've never heard of it before, it's not a real thing. But that's not how language works, right? COVID-19 was just a made-up word, right? This is a word somewhere around the 11th of February 2020. This word was used to describe a new virus. There wasn't COVID-19 before. And so just to say words can't be invented, I think in itself isn't a reasonable objection. Second objection is that things don't change color based on observation. And we might remind ourselves of this internet sensation of a couple of years ago where this dress under slightly different lighting conditions and to different people appeared to be two different colors. And, what do we think about that? And there's lots of sort of, the biology of color perception and the sort of philosophy of color perception both of those things are very complicated, right? We like to think that the color is a feature of the dress, but in fact it is a feature of our perception of the dress. But none of that really matters, right? Right. So this person thinks colors are something we made up in our heads. Well, if that's true, what does that tell us about preferring green to grue? If green is something we've made up in our head, why can't grue be something we've made up in our head? Because what we're trying to do to say Goodman's articulation of the problem here is flawed is to point out, essentially, that it comes down to why is grue a bad concept and green is a good concept. I'm not sure we've found that yet. So I would say really this whole color, things don't change color thing is a bit of a red herring. That takes us down a long and winding road that really isn't well, it's a fascinating and interesting problem, but it's not today's problem. Goodman isn't saying that color is any specific thing. He's just, in fact, his answer to this is, look, I'm defining grue in terms of green, and so whatever properties green has, grue has those properties too, and then I'm also defining it in terms of blue, so whatever properties blue has, grue has that too. So, he's kind of, it's a bit of a punt, but I think it's rational. So what's really wrong with being grue? We might say, look, this is not in itself a color. This is if it were a color, it would not be the sort of thing that fundamentally changed, right? It doesn't depend on observation. And Goodman himself sort of anticipates this objection in his paper. If you can't define color in terms of observation of color, and or any color defined in terms of another color is not really a color, which, certainly not the way people talk about color, right? You're talking about which shoes you're going to wear or what color you should paint your house. It's like, I want a slightly less green brown, right? So we talk about colors in terms of other colors all the time. So remember the original definition, let grue mean green when observed and blue when not observed. And Goodman also introduced the concept of bleen, which is blue when observed and green when not observed. And he points out that if your objection is something's illegitimate, if you're defining a concept is illegitimate, it's not a real concept, if it's defined in terms of another, he points out, well, actually, I can define green and blue in terms of other colors. So he said, look, I'm gonna define what I mean by green, Mr. Nelson Goodman here. When I say green, I mean grue when observed and bleen when not observed. So if you're telling me a color is not real if it's defined in terms of another, well then there goes your concept green, because I just defined it in terms of another. And I think that's a bit of a pretty solid response. So I think we still have a real problem here. And writing when he did, I think it's pretty deliberately, and I think it's pretty obvious that Goodman had in mind the fact that the theories much in vogue at the time in physics, and they're still in play today, predict uncertainty of properties based on observation. It turns out, according to the quantum theory that was much in play in his day, that you could predict either the motion or the mass of an object, but not, and these are like, molecular, tiny things, right? This is the stuff that physicists like to play with. That you couldn't predict perfectly both of those things at the same time. And that led to the Schrodinger's cat thought experiment, where inside a box there would be a mechanism, and it was, Schrodinger describes it as a hammer that breaks open a vial of poison gas, and that is triggered by the release of an atom from this radioactive box here. So now, Schrodinger's point is, since the radioactive decay is not predictable, until you look in the box, you don't know if you have a live cat or a dead one. And that somehow it seems like you've got an alive cat and a dead cat at the same time. And fortunately, Tiger's not here to hear all this horrible news about cats. Schrodinger was actually proposing that this is, Schrodinger was arguing that quantum theory is obviously bad because you can't have a cat that's both alive and a dead at the same time. That's a contradiction, right? And so, but it's that sort of predictability and observational dependency that that Goodman has in mind when he's trying to set up this grue-bleen problem as a way of explaining Hume's problem of induction. And this is going somewhere. Bear with me. It's a bit of a long walk, but it's going somewhere. Now, so in the same, so that we have a blue and a green cat here, so to speak, right? So it's alive when observed and it's dead when it's not observed. So the concept of grue just seems wrong to us. And I think we can put our fingers on the problem, which is that we don't think something stops being green, whatever green is, or doesn't stop having the capacity to appear green to a human observer when no one's looking. And if you've always thought, a tree falls in a forest, will it make a sound if there's no one here? And you thought that was the most quintessential philosophical problem. Well, that's basically where we're at, right? If something's green but no one's looking at it, is it still green? Or could it be blue when no one's looking at it? And usually there's an engineering student in the front row who's going to build something to prove that it's green all the time. I'm going to keep a camera on it and we'll upload that to my Google Docs and we'll examine it later to see if it ever turned blue. And that's a lot of fun, but it's kind of misses the point, because suppose you had a video of a green object, and how would that look on the video? Well, when you looked at it, it would look green, and if no one was watching the video, it would be blue, because it's a grue object. So the fact that you're just going to watch it later, that's the point at which the observation happens, kind of besides the point. So why do we think things are green all the time and not just when we're looking at them? Well, Hume told us, and Goodman says Hume was right. The reason we believe that is because the principle of the uniformity of nature, that the properties objects have are, fixed and permanent and don't change based on our perception or our presence. So we end up in the same point, right? The reason induction works is because induction works. The reason things are green all the time is because nature is uniform. And the reason we believe nature is uniform is because every time we look, it's uniform, right? Why do we think green objects are green? Because every time we check them, they're green. Now, could they be blue when we're not looking? Totally. But we don't think so just because of our faith rather than evidence in the principle of uniformity of nature. So Goodman writes, as the principles of deductive inference, we have, this is the same quote, right? So this is just to remind ourselves where we've come from here. So why do we have no precisely and well-recognized principles of inductive inference? Because the whole thing is inherently circular. That every inductive argument starts by saying, well, it's always worked in the past, so let's just keep us counting on that. And there's two ways to go with this. There's some folks want to say, throw up their arms and say, I give up, we'll never know anything. And I think that's the wrong way to go here. However, and both Goodman and Hume say, listen, what we need to do is carry on with our lives, get on with our days, but understand that for every new bit of information that counts on induction, we're going to have to accept that there's an element of uncertainty and an element of Hume calls it faith, baked into that you're going to have to trust that you could be wrong and that you're making an unjustified assumption hidden inside your inductive argument. So now we understand why scientists can be wrong. Why a scientist would never claim, proof in any sort of mathematical way. I do occasionally hear scientists say, I've proven it, but boy, that's what they often mean is I've done a lot of work and I'm really, really sure. But they don't mean proof with mathematical certainty. So I think we understand a bit about why they talk the way they do. And so they sound to someone who hasn't thought critically about these things as if they're hedging their bets a bit. They say probably, likely, there's a margin of error. We expect, not we're sure. And so when we hear Dr. Rusin on making his claims on his news every day, when he tells us the bad news about COVID in Manitoba, or Dr. Tam telling us the same grim story about Canada, and then you look at the comments on Twitter or on Facebook, and there's incredible frustration about why they won't just tell us the truth. Why are they always hedging their bets? And why do they sound so evasive? Well, because they're making uh, their scientific conclusions based on an imperfect methodology. Every inductive argument is imperfect. And if they were to slam their fist on the table and say, this is absolutely the truth, that's when actually you should be super suspicious. So that's the new problem of induction. It's not easy to be grue. Next time, we're going to look at Mill's methods, and those will have a little less conceptual effort required to get it. So this is probably, we've just been through with Hume's and Goodman's problem of induction. I do it twice because it's hard, but actually we're from here on, it's all downhill. We can coast to the finish line. We understand the conceptual problem we have, and now we've got to essentially a series of philosophers of science who are going to propose interesting ways to try to work with what we do have with respect to induction. And the first will be John Stuart Mill and his methods of experimental inquiry. Have a great day.